Every plugged-in device loses energy before doing its job. The culprit is electrical resistance, dictating how we generate, distribute, and consume power. Inside a standard copper wire, electricity behaves like a traffic jam. Trillions of electrons are trying to move forward, but they are constantly smashing into the metal's atoms, which vibrate aggressively at room temperature. Every single one of those microscopic collisions generates friction. That friction is released as heat. Across global power grids, this atomic gridlock bleeds billions of dollars worth of raw electricity into the air every year. But certain materials possess a loophole in the laws of physics. They are called superconductors. They have the ability to carry direct current with absolutely zero resistance. Overcoming this intense atomic friction transforms our energy transmission from a wasteful, heat-bleeding process into one of absolute, flawless efficiency. Reaching this state requires pushing metals to their absolute limit. Physicists plunge them into vats of liquid nitrogen, dragging their temperature toward absolute zero. As the metal cools, it reaches a precise thermal threshold known as the critical temperature. At this exact point, the chaotic vibration of the atomic grid stops. The atoms lock still. With the atomic grid frozen, the electrical traffic jam clears. The electrons stop bouncing and link together, forming Cooper pairs. These paired electrons enter a superfluid state, gliding seamlessly through the stationary lattice and avoiding collisions entirely. If you start a direct current inside of a superconducting metallic loop, it will flow continuously for an absolute eternity. It will not lose a fraction of a volt, even after 1 billion years. Stripping away all the thermal chaos of the universe leaves us with a material that achieves absolute, frictionless electrical perfection. In addition to zero resistance, true superconductors possess the ability to actively reject magnetism. This is the Meissner Effect. As a material becomes superconducting, it forcefully expels internal magnetic fields. When a magnet approaches, it instantly generates an equal, mirrored magnetic field. The opposing fields clash, creating a high-pressure, empty gap. Physically, this invisible clash causes a falling magnet to stop dead in its tracks and hover effortlessly on an invisible cushion of opposing force. The Meissner effect turns a standard piece of metal alloy into an impenetrable magnetic fortress. Some materials, classified as Type II superconductors, contain microscopic structural imperfections. These tiny flaws trigger an even more complex physical anomaly. In a Type II superconductor, the material isn't perfectly pure. Thin strands of an external magnetic field actually punch straight through, using microscopic flaws as tunnels. Inside, these magnetic threads become trapped, a phenomenon called flux pinning. The field is held tightly by the holes. Because these threads are pinned tight, the levitating magnet locks in a fixed orientation. Even turned upside down, it remains frozen, completely ignoring gravity. The object is physically anchored to the fabric of space by invisible quantum threads. Harnessing these physics today comes with a severe bottleneck. Maintaining the state requires encasing the materials in massive, expensive vats of deep freeze liquids. That massive engineering cost makes the global hunt for a room temperature superconductor the ultimate prize in modern physics, a material that retains these properties without needing the extreme cold. Even with the thermal limitations, we already rely on superconducting magnets to generate the intense, flawless magnetic fields required for modern MRI machines. A future optimized by a room temperature variant means completely lossless global power grids and massive, silently hovering transit systems. Stripping away thermal chaos allows us to bypass the electrical losses that have constrained engineering since the discovery of the power grid.